Hello everyone, I am Agustin Nievas. I just graduated as an electronic engineer from Universidad Católica de Córdoba. I'm author of the paper titled Comparison of P&O method for MPPT in a real system with a synchronous back converter. Well, to start, solar power generator system require maximum power point tracking (MPPT) control for maximum performance. One typical method is the Perturb and Observe P&O algorithm. In other words, the objective is the maximum point of the power curve on the top right image. In the respective paper, different maximum power point tracking algorithms are presented, all based on the Perturb and Observe method, and they are implemented in a real solar photovoltaic to facilitate the change of algorithms and data collection. The presented MPPT algorithms were implemented and tested using an ESP32 microcontroller, controlling the duty cycle in a DC-DC synchronous step-down converter circuit. So we can focus our attention on how the maximum power point tracking controller has four properties. It implements a certain method algorithm to track the maximum power point, like Perturb and Observe. Has a topology electrical circuit that works as an interface between the method and the environment. In this particular case, an ESP32 microcontroller is used to implement the method in reality, because every element in this paper are real and have been physically implemented in the field. I will start with the method Perturb and Observe. Basically, it's a method that changes the control variable and reads the output. Well, one can change in a positive way this variable more than negative. It can be balanced or decrease the variable stronger than increase it. Meanwhile, one can limit the method using a reset that control variable based on values saved on a memory. Meanwhile, one can limit the method resetting the control variable based on values saved on a memory, or just save a reset based on values in a memory. To illustrate this better, here are flowcharts of Perturb and Observe algorithm. So first, one measure and save the output power. If this power is greater than before, the method increases the control variable D, duty cycle of the back converter. If the power is lower than the previous one, the method decreases the variable D. After this change in D, the system power changes, and finally the power that was measured at the beginning of the method is saved as the previous power, so the method repeats. As you can see in these three charts, they theoretically work the same way, but one can increase or reduce the resolution of the control variable from a half percentage change to 1% change, or have the method with larger increase or decrease by having different percentage on either side of the change. Now I will show a different view of these previous flowcharts, and it is a memory limit. This extra part of this flowchart only resets the D variable on the D minus 1% with the largest power. At the start of the method, the power is saved in an array of values, and after 10 of these, a normal quick array maximum value research is implemented. This change can contextualize the best cycle over the large scope of just two power values, the actual value and the previous one. And one can also just implement this change by 1% 10 times and change the start of these values in a new D minus 1% corresponded to the maximum power of the power array. I call this method memory. It's basically the Perturb and Observe method with more information of mere forward values. These were the methods that are implemented, and all of these run on a ESP32 dev board that has a function to easily translate from variable D in percentage to duty cycle on the topology of the synchronous back converter. Because of the totem configuration in this converter, an AR2110 MOSFET driver is used, and to measure the output power, an Arduino high current sensor with a resistor divider is used. To end this first part of the presentation, I will repeat myself by saying all the elements have been physically implemented in the field. With this real implementation, the following curve is obtained. Experimental results effectiveness is measured against the duty cycle graph, serving as a baseline for comparison. Therefore, a duty cycle of 75% is viewed as the maximum power point possible, and a duty cycle between 55% and 90% is considered functionally inefficient. The curves given by the method P&O with larger increase are the following. Where the duty cycle converges at 100%, is considered neither functional nor efficient. The method P&O balance has a duty cycle that converges at 0%, is considered neither functional nor efficient. When implemented the method P&O with larger decrease and memory, the duty cycle has an average value of 55% and a maximum of 60%. This method is considered functional, but not efficient enough. The method P&O balance and memory has a duty cycle that converges at 60%. Thus, this method is considered functional and efficient. The final method, just memory, has a duty cycle that converges at 60%. Thus, this method is considered functional and efficient. To conclude, the results are compiled on the following table. As the value of 75% is taken as the best MPPT method performance point, then the method P&O balance and memory, the method memory, are the best method that best approach the objective of 75% as it can be read. 80% is greater than 73% or 66%. With this, it concludes that not any P&O method does converge correctly, and that a variable duty cycle resolution or a memory limiter may be necessary for a real system implementation. Thank you very much and have a nice day.